that brings us to final projects. It's, time flies. There's already time to be thinking about final projects, and in particular, you should be forming your teams. And there's a Google form that we put up. The link is there. We'll post this on the webpage and on Piazza. So sometime before next Tuesday night, so a week from today, you should have figured out what your team is. Not necessarily what your topic is, but what your team is, and put that information there, who's on your team, in the Google form. And if you're not able to form a team by then we're going to look at who's unassigned or who doesn't have a team, and then basically randomly group those people into teams of 3 or 4. If you have one person you want to work with and you can't find anyone else, then you can sign up in this Google form with a team of 2, and then we're going to add, to make it teams of 3 or 4. But preferably self-organize, in person if you're local, and on Piazza if you're online or local. Find your teams and put the information there. So that's due a week from tonight, a week from tonight, okay? So, and of course, be thinking about what type of topic you might want to work on, which also affects who you might want to work with, because you can find people with similar interests. You can work with your friends if you have friends in the class, but you could also find people with similar interests or complementary skills to work on a specific topic that you're interested in. So, okay. And of course, homework 4 due next Thursday, 11:59 p.m. as usual. Start early if you haven't started. Okay, so this week is all about Bayesian thinking. Starting from very beginning basic Bayesian concepts. It's one of the major schools of thought for statistical problem solving. It's been controversial for hundreds of years, and I'll explain some of the controversy, and I'll try to explain why I don't think it should be such a big controversy. And I don't want to get into the philosophy a lot, just more about why is this a useful approach and how can you use it, starting with no knowledge of Bayesian statistics to being able to, it's a big topic, and we have entire courses on Bayesian statistics like Stat 220 in the statistics department here, and various other Harvard courses that go into further depth in these methods, but this is sort of like a 1-week crash course in Bayesian statistics. And I'll do what I can. But keep in mind, it's a huge subject. It's an active research area. In 1 week, we'll be able to cover enough so that you can implement some basic Bayesian models, and you can actually do some non-trivial, interesting calculations, interesting simulations using these methods. You can do some, fairly realistic, nice models. But at some point you'll get to bigger and bigger, more complicated models and more computational challenges, and then that's, more than we can deal with in a week. So here's a few recommended Bayesian references, since obviously there's a limit to how much we can do in a week, so if you're interested in going further. I listed a few books that I like. They're not required reading. I don't expect you to read 4 books, but for those of you who are interested in going further, these are some recommended references. From easiest to hardest. This is the easiest one. This is a popular book. It's almost no equations. It's written for the general public. It's called The Theory That Would Not Die: How Bayes' Rule Cracked the Enigma Code, Hunted Down Russian Submarines, and Emerged Triumphant from 2 Centuries of Controversy. Okay, so that's a very impressive sounding title. And it's a little bit hyped, but it's true that there have been 2 centuries of controversy, and one of the key breakthroughs with cracking the Enigma code was the work of Alan Turing, which has become very, very famous recently, deservedly. Turing was one of the greatest geniuses of all time. And a lot of that work during World War II was classified, but some of it has been gradually declassified, and basically Turing was inventing Bayesian statistics on his own. And then because that work was classified, it was kind of rediscovered and re-implemented in different ways independently. And anyway, this is a really nice popular book about Bayesian thinking. This one is a free book, and it's in Python, and it's free, by Alan Downey. I like it a lot. It starts with, very, very simple examples, explains things in a very clear, simple way. Here's how you do basic Bayesian statistics in Python. The downside is also that the simplicity in that, you quickly will run into models that you can't deal with using the methods in this book, so, you'd have to go further. And then one that's a little more advanced, but also starting with very basic stuff, is probabilistic programming and Bayesian methods for hackers. And this book is also free online, and it's all, the URL is here. And it's all in Python and actually IPython notebooks, and it's a book, but also in IPython notebook form, so that's very convenient for the type of stuff that we're doing. And this one is the only statistics book I've ever seen with puppies on the cover. Doing Bayesian data analysis, this one is not free, but it's a really good book, so I still recommend it. That right there on the cover, underneath the puppies, that's Bayes' rule. And we'll talk about, this is just, Bayes' rule is this simple-looking equation that has these profound implications and applications. And at first I thought he just must really love dogs to put these, and he's trying to be friendly, of course. This is supposed to be, the friendly version of Bayesian statistics. But actually, he wrote about, he wrote a description of why he chose which dog corresponding to which of these items in this equation. And we're going to be getting into all this stuff, but this term here, P of theta, is called the prior on theta. Theta is your unknown parameter, okay? So you're trying to estimate some unknown quantity, and we represent, in statistics, we often call those unknown parameters theta, or call it whatever you want. That's what you're interested in estimating, this theta. P of theta is your prior. That's before you have any data. This is quantifying your uncertainty about it. Now, this term here is called the likelihood, and we'll talk more about that. And this is the posterior. Again, we're going to talk more about that. Posterior means what should happen to your beliefs about the unknown given the data, D for data, right? So given the data, what do you then think? And I think he chose these dogs to be so that the posterior is kind of a compromise between the prior and the likelihood. Like this dog's ears are down, this dog's ears are up, these ones are kind of halfway. Right? So this dog is supposed to be a compromise. You can look at the color schemes and so on. It's a compromise between this dog and this dog. So it's a really good book. It's more accessible. This is called Doing Bayesian Data Analysis. This many people refer to as the Bayesian Bible, Bayesian Data Analysis. We use this as our textbook in Stat 220, which is a course I highly recommend for the on-campus students. There isn't a DCE version of it currently, unfortunately. But you can still read the book, whether you're a local or extension student. I highly recommend this book. It's more, this is a 700-page book, and it starts from beginning stuff, but it ramps up pretty quickly in complexity. It assumes some familiarity with, like, linear regression and basic probability. And, it's what I would call a very modern treatment of Bayesian statistics. Bayesian statistics goes back, in some sense, to Bayes himself, who was a Presbyterian minister and worked on this stuff 250 years ago, but he wasn't thinking at all about the machine learning. He wasn't thinking at all about the modern types of applications that we're doing, and he would have never predicted how those ideas would evolve. And then a lot of the history of Bayes has been plagued by these philosophical controversies, and this book tries to avoid philosophy for the most part and just show that this is a useful way of thinking. And don't worry about the philosophy. Okay. So here's Bayes' rule. This was some neon sign somewhere. I don't know why they chose that. But it's a simple looking equation. And so what's all the fuss? Here it is written more normally. P of A given B is P of B given A, P of A over P of B. If you write down the definition, if you haven't taken Stat 110 and haven't seen conditional probability much before, you can, find a review of that, like in the Stat 110, watch 10 minutes of conditional probability lecture. This is the very beginning of conditional probability. You write down the definition of conditional probability, and you derive this with one line of algebra. So this is an immediate consequence of the definition of conditional probability. It's not a deep theorem at all. It's just simple algebra. So it's kind of mysterious in the sense that this is just a very simple theorem of algebra. And why is it so useful, and why is it so controversial? And the interpretation here is that you're interested in quantifying the probability of some event A. So you start with this prior P of A. That's the probability of A before you have data, and then you observe something. So in this case, you observe that B occurred. Okay, so now you want to update your beliefs based on the fact that B occurred, and Bayes' rule tells you how to do that. So Bayesian statistics is full of talking about prior versus posterior, and that's the biggest distinction to keep in mind. Prior is before you have data. Posterior is after you have data. Here's how you update. And it's generally sequential in the sense that, imagine you're a detective and you're going around, looking for clues, right? To try to figure out who's guilty of some crime, and you get the first clue. Bayes' rule tells you how to update your evidence based on that clue, but then you don't stop there, right? You keep trying to get more evidence, more data, right? Find some more fingerprints, things like that. So you get another clue, you use it again and again sequentially. And it has this nice coherency property that says, let's say you have 5 pieces of evidence that you find at a crime scene. You could just take all that evidence and do Bayes' rule once to update your beliefs about the probability that a certain person is guilty, given all the evidence. Or every time you notice something new, you could update then, right? And what happens if you do it sequentially is you start with a prior, that becomes your posterior after you update. Then that posterior becomes your new prior. And then you get more evidence. And you again compute a posterior. And again, that posterior becomes your new prior. And you keep doing that. So you use, your posterior tonight is your prior tomorrow, right? And then you keep going from prior to posterior, prior to posterior. And it's this very simple equation telling you how to do those updates. And let's write it in a more statistical form. This is the exact same equation again. I just changed the A and B to theta and y. So it's the same equation. But in statistics, we typically would call our data x or y, and we typically call our unknowns theta. So this is all about getting the posterior distribution of unknowns given knowns, right? We have the data, we don't know the parameters, so we want to do this kind of update. So that's just Bayes' rule again. Again, it shouldn't seem too controversial, so I'll tell you a little bit about where the controversy comes from, and then I'll quickly try to get away from the philosophical debates. So let me rewrite that a different way. Let's ignore that denominator on the right-hand side and just work up to proportionality, because this is often how you do it in practice. If you wanted to work everything out mathematically, that denominator, P of y, is often the hardest thing to deal with, because the usual way we compute that is with some big sum or integral that comes from the law of total probability, and that integral is often intractable. But a beautiful fact is that often you don't actually need to compute that denominator. So if we just work up to proportionality, we're thinking of the data as fixed, because the data is what we actually know, right? So the data is what we observe, we have the data, and the Bayesian approach says theta is what we don't know, we're going to give it a distribution. So we're using probability to quantify our uncertainty, which makes sense, right? Because probability is our best language for quantifying uncertainty. So we're going to quantify it with a distribution. And if we think of y as fixed, then that denominator is just a normalizing constant. And so the posterior density of theta is proportional to the likelihood function times the prior. The likelihood function, L of theta, that's just the P of y given theta. So P of y given theta is the density of the data. But in statistics, in everyday English, people use likelihood and probability interchangeably. In statistics, likelihood is a technical term. Likelihood specifically means that you're taking the probability of the data given the parameter, but you're viewing that as a function of the parameter, which is kind of a flipped way of thinking from what you're used to a lot of times in, a first probability and statistics course. When you start out in probability statistics, usually you're thinking of theta as fixed, and you're thinking of this as a function of y, and you want it to sum or integrate to 1. When you're doing statistical inference, this was Fisher's big breakthrough, was that you want to look at it the other way around, as a function of theta. So that's called the likelihood function. The likelihood function is the probability of the data given the parameter, but as a function of the parameter, holding the data fixed. So we have talked about maximum likelihood. Maximum likelihood just means take this likelihood function and find the value of theta that maximizes it. Okay? And Fisher showed that that has a lot of really nice properties. But it's not a panacea. Okay? We've also seen problems where maximum likelihood does something pretty stupid, and you want to apply shrinkage or regularization ideas, and you can do a lot better. Okay. So that's the statistical inference view of Bayes' rule. It just says that the posterior distribution is proportional to likelihood times prior. That's all there is to Bayes' rule. So why is there all this controversy? And this is just assuming you accept the definition of conditional probability, which most people do, that's just a theorem. You can prove it in one line. So it seems like there shouldn't be so much fuss about it. The reason that there's fuss is that the traditional frequentist view of statistics has been that theta is an unknown constant, and they're very uncomfortable with giving it a probability distribution. And the Bayesian says, well, it's unknown, we want to quantify its uncertainty, probability is our best way of quantifying uncertainty. But the frequentist says, theta doesn't have a distribution, it's just a constant, and it's not random. Right? So a Bayesian is effectively treating everything as a random variable. And frequentists don't want to give theta a probability distribution. So that caused many, many nasty, vicious debates for hundreds of years. And the other big part of that controversy is the prior. This thing, P of theta, where does it come from? Right? If you accept the prior and the likelihood, then that's just a theorem. That's your posterior distribution. That's your the best thing that you can say about your parameter given the data. But where does the prior come from? Okay? So that's been debated for centuries. And you'll find some Bayesians who say the prior is just your subjective degree of belief for theta, right? So then they're thinking more in terms of rational agents, right? You can imagine that you want to, make decisions in life and you want to figure things out in your own mind, right? So that school of thought, there was an article, by the way, called something like, I don't know, I forgot the number, like 127,000 varieties of Bayesian, some huge number, trying to classify Bayesians. So there have been a lot of debates even within Bayesians that basically have to do with subjectivity or objectivity. A lot of it comes down to this prior. Okay, so there are the people who call themselves subjective Bayesians who say, that's just your degree of belief. I can have my degree of belief in theta. You can have yours. You can each have your own prior. And if we agree on the likelihood and we agree on using Bayes' rule, then we're going to do this thing. But we're all going to get different answers, and it's subjective. And those types of Bayesians will often say things like, it's coherent, right? It's a rational way to think. No one's ever going to prove that that's the wrong way to do things. But that's not very satisfying to people who want to do science and say, like, actually, can we come to some sort of agreement on ways to do things that feels less subjective? Okay, so there are all kinds of philosophical debates about subjectivity or objectivity. And then the other response is, yes, P of theta is subjective, but so is L of theta. Everything is subjective, right? Because except in the very simplest problems, all models are wrong, but some models are useful. So except in the very simplest problems, you don't really believe you have the correct likelihood. You made some subjective choices, right? So anything you're doing, you're making some subjective choices about what to do and what to model and what model to use. And a nice fact is that two people can start out with different priors, but if the sample size is reasonably large, then and their priors are not ridiculously dogmatic. Like if your prior is that you're 100% sure that theta equals 3, no amount of evidence is ever going to change your mind, because you just made up your mind already that theta is definitely 3, okay? But if you're not so dogmatic like that, as you get enough data, you will eventually converge to the same thing as someone else who started out with a different non-dogmatic prior. So, there are theorems along those lines, but it makes sense intuitively that what's going on is that if the sample size is large, this part, the likelihood function, is going to dominate over this part, the prior. So unless you have a ridiculously strong prior or a very, very small sample size, the likelihood is what really matters. The likelihood is also involves some subjective choices. So I think that the modern point of view that's exemplified in the Bayesian data analysis book is that we should focus on our likelihood function, okay, trying to get a reasonable likelihood function. We should try to choose a prior that's not going to be ridiculously dogmatic, right, so that the data can speak up for itself. So we give the data the opportunity to speak up for itself, and we don't worry about kind of these philosophical controversies. Of course, you'll run into trouble if your sample size is small, but that's true for anything you do, right? If the sample size is small, do whatever method you want. You're going to expect that different methods are going to disagree, okay? The hope is that if you have a large sample size, then different reasonable methods will agree, and that tends to be the case. Small sample size, all bets are off, okay? So that's Bayes' rule, and it's just a mathematical fact as long as you're willing to give theta a distribution. All right. And so let me just briefly describe what does this say in terms of classification to tie this to some things we did earlier. So there's a distinction between a discriminative and a generative classifier. And that kind of gets at one of the most fundamental questions in all of statistics, right? Like, I think we could come up with a list of 5 or 10 questions that pervade all of statistical methods. And one of those questions that should be on the list is, what do you want to model and what do you not want to model, okay? So, in principle, philosophically, you could say, well, just model everything, right? But in practice, every time you're creating, models, it takes effort, right? It takes mental effort, it takes computational effort. You don't want to have to model everything, okay? So in a discriminative model, you just focus on, so suppose we're using x's to predict y's. So if it's a classification problem, we think that we have some features x, and we're trying to divide individuals into groups where the labels are given by y. And so we're just in the discriminative case, we're just focusing on p of y given x. For example, logistic regression fits into that. So we're trying to predict the probability of a 1, binary, right? Probability of a 1 as a function of the x's, but we're not giving a distribution to the x's in that case. So that's not a Bayesian thing. You can do Bayesian versions of logistic regression, which have some nice properties, but logistic regression, as we did it, is not Bayesian at all, and we're not modeling the x's. We're modeling the distribution of y given x. In a generative model, we're doing a full model for how you could generate data. So that's why it's called generative. If you have a generative model, you could go and simulate the entire model. you could generate new x's and new y's, right? So you could generate x's from some distribution, and then you could generate y's given x's. And you can go, this is actually just another way to write Bayes' rule. So this is, the joint probability. What's the probability that the x will be this x and the y will be this y? And you can either go p of x, p of y given x, or you can do p of y, p of x given y. Again, this just follows from the definition of conditional probability. So if you wanted to simulate from such a model, you can either generate x's and then generate y's from the conditional distribution of y given x, or you could go the other way around. So it's a full model. So for example, in the classification context, let's suppose we have two groups, y equals 1 and y equals 0, like in logistic regression. But in this case, unlike logistic regression, if you want the probability of y equals 1 given x equals x, and what I wrote down here is just Bayes' rule, and I expanded out the denominator. The difference is that you are then looking at what's the probability of each value of the feature within the two groups. So you're flipping it around. So let's take a simple example, and this also explains the concept of naive Bayes. Okay, so suppose we're trying to build a very simple spam classifier for email. So I want to classify, is email spam or not spam? And kind of a natural way to do that is to look for certain words or phrases that occur very frequently in spam, but not so frequently in regular, legitimate email, right? Like, free money. Get a lot of spam, about some kind of, you just won the lottery, right? That kind of thing. Get a lot of spam about Viagra, stuff like that. Okay, so you could, if you have some database of spam and legitimate emails, you could go through and see which words appear a lot in spam that don't appear often in legitimate email. And let's say, just for simplicity, suppose we made a top 10. I just wanted to make up a simple, concrete example. I said, okay, let's make up, let's say we had a top 10 list, and those are the WJ. So WJ is the event that the jth keyword. So we made a list of 10 words that occur often in spam, but not often in legitimate email, and let WJ be the event that the jth word appears in the email. So obviously, if we see that word there, then it increases our chance that the email is spam. Okay, and then suppose we just got a new email, and we want to classify is it spam or not spam, and we notice through scanning the email that it uses the first and the 10th words on this list of 10 and doesn't use the other 8. Well, how can you find the probability? It's just Bayes' rule. So I wrote down Bayes' rule again. The probability of a spam given, and that event there on the right just says the first, C is complement. So that means that the first keyword appeared, the second one did not, third one did not, and so on, and the 10th one did. That's just Bayes' rule. P of spam is the prior probability of spam. And prior, you don't have to get into a big philosophical controversy about what's the prior probability of spam. You could just imagine you just have some prior, that's why it's called prior, right? You imagine that you have some prior data, and in the case of email, you could really get some training data like that, and what percentage of past emails that you've gotten are spam. So I would use that as my prior. And the denominator might not be obvious how to find it, at least if you haven't had Stat 110, but there's a simple way to expand the denominator, which is law of total probability. So it's just a way. In this case, there's only 2 terms. If you expand out, I'm just abbreviating this whole big thing to W, and it's P of W given spam, P of spam plus, this is called the law of total probability. In this case, there's only 2 terms, so it's easy. In general, I was mentioning the fact that in Bayesian statistics, the denominator is a pain. Because in general, instead of having 2 terms there, you might have, a trillion terms, or you might have an integral, and you might not know how to do that integral even if you've taken a lot of calculus classes. So it might be a high-dimensional, complicated integral. In this case, though, it's just 2 terms, so it's very simple. The problem, though, is how do you actually feed into these? How do you actually find this thing? What's the probability, given that an email is spam, what's the probability that it uses this keyword and this one, but not the other 8? Now, that's actually very annoying, not doing one of these, but the problem is I just made something up here, right? I just picked that this keyword appears and this one appears and the others don't. But I could have chosen any other combination. So there's 2 to the 10th or 1,024 such things I could have chosen. I could have done W1 complement, W2 complement, W3, W4, or whatever. All right, any choices for which subset of these 10 words appears, there's 2 to the 10 possibilities. So I would have 1,024 things that I would need to know how to deal with here. And that's for 10, right? If you had more realistically, you might choose the top 100, not the top 10 keywords. And then I would have 2 to the 100 things that I need to estimate here, right? So that would be a computational and statistical nightmare. How would you deal with so many things? It grows exponentially. So here's the naive Bayes assumption. The naive Bayes assumption is a conditional independence assumption. It says that the probability of all of these W's, that is the first keyword appears and the second one doesn't, and so on, just factors. So it's P of the first thing given that spam, P of the second, you just multiply them. If you're familiar with the definition of independence in probability, this is just the definition of independence, except I made it conditional, given that it's spam. Similarly, given that the email is not spam, the naive Bayes assumption is just that you factor it. And so notice that this has a huge simplification that now I just need to know what's the probability that, let's say that W1 refers to mentioning free money. I need to know what's the probability that a spam email will mention free money, and what's the probability that a legitimate email will mention free money. And I need to know those, for all 10 things, I need to know that. So I need to know like 20 different things, not 2,000 different things. So it's a huge, huge simplification. But does that actually make sense? So I said here, a huge assumption, but huge simplification. Naive Bayes doesn't mean that Bayes is naive. It's a naive model, okay? The Bayes is just the Bayes, okay? So we're using Bayes' rule. The problem is that it would be a nightmare dealing with so many different terms that could appear there. So we make this conditional independence assumption, which is a very naive assumption. But often it works surprisingly well. So this is a paper. I have a reference to a paper here that I like that's comparing different classifiers. And this was just an example where naive Bayes did, this is just one example, but the paper is pretty thorough in kind of comparing different models for some interesting realistic examples. And it often does really well, even compared to state-of-the-art, very, very fancy, complicated methods, even though it's so simple. And it's kind of like a, Occam's razor type of thing that, all models are wrong, but some models are useful. And oftentimes a simple model is not only more interpretable, easier to implement, easier to understand, but it often actually works very well too. So that's what naive Bayes is doing. Okay, so I wanted to read just one quote for today that kind of motivates everything in Bayesian statistics. This is from the very beginning of the Bayesian data analysis book. So I actually think that a better name for Bayesian data analysis would just be full probability modeling, right? So the question is just, what do you model, what do you not model? For Bayesian, you model all of the ingredients of the problem. Not that you're modeling the entire universe, but you're working on some problem and you have different variables in there, and you just create a full probability model for them. Okay, so the focus is not on whether you're using Bayes' rule or not. The emphasis should be on what do you want to model. Okay, so Bayesian creates this full probability model, which they defined here as a joint probability distribution for all observable and unobservable quantities in a problem. Okay, so normally in statistics we divide things up as data and parameters, but we could also, actually I wouldn't have just said observable and unobservable, I would say observed, observable, and unobservable. The distinction being, so we have these parameters, theta, that a parameter doesn't really exist usually, right? It's the parameter is just some theoretical thing that goes into the model. It's not something that you could ever actually observe, right? Even in principle. Like a regression coefficient, beta, right? You have linear regression. You know, y equals beta 0 plus beta 1x plus epsilon. We know that that model is wrong anyway. So what do those betas really mean, right? They're just, you know, they have an interpretation, but what does it mean to estimate the parameters for a model when you know the model is wrong? You know, it gets into some philosophical questions that I actually don't want to get into. But it's worth thinking about, though. What do the parameters really mean? So parameters are unobservable, even in principle. And then there's also stuff that you observed, of course. That's your data. But there's also stuff that you could have observed, but you didn't. And a common example of that is missing data, right? So with missing data, you wish you had observed that data, and you could have, but it just happens for any number of reasons that you didn't, right? So that, you know, could have been observed but wasn't. And also future data, right? You can use Bayesian statistics as a very powerful way to make predictions about the future. And the best part about predictions is then hopefully you can actually check. You know, right now we don't know the future, but then we get to observe the future and see how well did our predictions work. Okay? So future data is observable, but it just hasn't been observed yet. So anyway, we set up this full probability model for everything. The parameters, the observed data, the unobserved data, the missing data, all of them together jointly. They're given some joint distributions. If you've taken Stat 110, you're very familiar with joint distributions. If you haven't taken Stat 110 or something like that level of probability, joint distribution just means you're simultaneously saying, you know, what's the probability that the data will be this, and the parameters will be this, and the future data will be that, just together in one model, all of those things, okay? And then condition on the observed, so that's step one. This is the three-step version of what Bayesian data analysis is. As I said, it's a 700-page book, but this is a brief summary of the Bayesian process that then, you know, you can go through many examples, and there are a lot of implementation difficulties when you get to more complicated models. But this is the outline of the way of thinking. Okay, so then you condition on the observed data. So that's step two. Bayesian says, the only thing we actually know is the data, all right? So let's condition on the data. So we're going to look at the distribution, the probability distribution of unknowns given knowns, right? We're going to look at the probability distribution of the stuff that we haven't observed or couldn't observe given the data. And that's where you can see very cleanly this frequentist Bayesian divide, that frequentists are focusing on the distribution of the data given the parameter, and they won't even write it in that notation because they don't want to treat the parameter as random. So the focus for a frequentist is on P of y given theta, and for a Bayesian, it's completely flipped, P of theta given y, okay? And they want to do it this way because we just condition on what we actually observed. Okay, so we interpret the appropriate posterior distribution. So most of Bayesian statistics involves trying to compute a posterior distribution and interpret that posterior distribution. So we get the posterior distribution. That could be the posterior distribution of the parameters, so P of theta given y. But it could also be the posterior distribution for predictive quantities. So we have something called the posterior predictive distribution, which is the distribution of future data given the observed data. So that doesn't refer to parameters, okay? And if you wanted to simulate the posterior predictive distribution, there's a natural way to do it. You say, okay, I have my data, and if we have the posterior distribution of the parameter, then you go like, you can use your data to generate draws from the posterior distribution, that's theta given y, and then for each of those thetas, then we have the data generating distribution, and you could generate fake data. So you can use that in several ways. One is to predict future data, what would future data look like? And then another way is just kind of to do some sanity checking. Like if you generate some fake data, the problem with the parameters is you're never going to know the true parameter value except within the context of a simulation where you programmed it specifically, right? For a real world problem, you don't know the true parameter value. And so, you know, if you construct a posterior distribution, it's kind of hard to assess, does that even make sense? But if you instead generate, you know, replicated data, so basically fake data sets, and then you can compare it with your actual data and try to get some sense of what's going on. Okay, so that's the second step. Second step is where the Bayes rule fits in, because the second step is why it's called Bayesian, because typically you're using Bayes rule to compute this posterior distribution. And then lastly is the checking step. So evaluate the fit of the model and the implications of the posterior distribution. So, you know, we've been talking throughout this semester about the importance of checking and communicating your results and doing sanity checks. And some of the old school Bayesians put all their emphasis on step 2 here and just said, okay, I'm coherent, so, you know, if you think of it in this subjective way where, you know, here's my old belief, got some data, here's my new belief, okay? And they stop there. And, you know, that's a pretty limited viewpoint. And this is saying you want to go further than that and actually check whether your results make sense, right? Just because Bayesian thinking has these nice philosophical coherency properties doesn't mean you shouldn't actually make predictions and actually see how well does it actually do, right? How well does it perform? Okay, so the more modern approach to it is that we actually want to get results that we can check and not just, you know, use this for our own internal consistency. So my slogan when I'm teaching inference is think like a Bayesian and check like a frequentist. That you don't need this holy war, right? And this simple Venn diagram is illustrating that just conceptually a fact. There are, you know, we're not going to prove theorems about this, but there are theorems along these lines. There are theorems that say that a frequentist procedure that doesn't have, so to interpret this, the yellow circle is frequentist procedures, and the blue one is Bayesian procedures, and of course, yellow and blue make green. The intersection is procedures that are good from both Bayesian and frequentist standpoints. And my argument is that you want to be in this intersection here. You want methods that are good from both points of view, and there are mathematical theorems to back that up that say if you're performing a frequentist procedure that does not actually have a Bayesian interpretation, like you may have come up with this thing without thinking at all along Bayesian lines. And then you could see, is there a Bayesian interpretation? And there's actually a theorem, roughly speaking, that says if there's no Bayesian interpretation, then that method is inadmissible. That you can actually find a method that's going to do better in terms of whatever loss function you're using. And, you know, going the other way around, you could come up with some Bayesian method, the method's like right out here, that where the prior you're using dominates over the data, and, you know, you have some kind of stupid dogmatic prior, for example, and it's not going to have good frequentist properties, and that's not good either. So, you know, we want methods that work well for the problem at hand, and we want methods that work well in the long run, right? So, like, we want methods that can be reused by many people in many contexts, so we want good long-run performance. So the nice thing, I should have actually drawn this intersection region to be bigger, more overlap. It's often the case that methods that, you know, created one way will be good from the other vantage point. And when possible, you should try to check it. So, for example, traditional, my own leanings are more Bayesian, but I have a lot of criticisms of traditional Bayesian stuff, in particular that they traditionally didn't focus much on prediction and validation and things like that. Like if you read most of the Bayesian literature, you're not going to find cross-validation. They don't generally use that, and I think that's a mistake, right? So I think, Bayesian thinking is a very powerful way to come up with methods, and there are a lot of problems where, if you have some frequent, typically speaking, this is kind of, stereotypes, but kind of generally what I've observed is you're faced with some problem, and if you're thinking entirely like a frequentist, it's pretty hard to figure out what to do, and eventually, hopefully, you figure out something to do, and then something in the problem changes, like two things that originally you assumed they were independent, and you realize that's not a good assumption, they should be correlated, right? Or you need to account for missing data or something like that. And then at that point, usually you don't know what to do, right? Like, take the bootstrap. Bootstrap often works really, really well with independent data, and then as soon as you get correlated data, it's really hard to figure out, like, what do you do with it? Every procedure has assumptions, okay? So the Bayesians just make those assumptions more explicit, and the fact that it's more explicit actually makes it easier to extend the model. So if you have some Bayesian model you're using and it's not working well enough, then usually it's not that hard to find ways to introduce another parameter or modify the model. So in a sense, it's more closely tied to the domain science, where you can kind of see more directly how to tinker with the model. But you have to do that checking. And so, I would like to see more Bayesians who, make predictions, do cross-validation, things like that. There's no reason you can't do both. So hopefully that will be the modern way that the field of statistics and machine learning that they head in that direction is what I'm hoping. Okay. So I don't want to get into a lot of math today, but at least to give you a few concrete Bayesian models. Let's start with one of the simplest, but still very, very useful ones, which is a binomial. Okay, so we reviewed the binomial distribution before. I'm assuming you all know that. But we haven't written this notation before. X given P is binomial NP. Usually we just wrote binomial NP. So that there's countless problems where you're interested in, you observe data that's some proportion, right? So there's some number of trials and some number of successes and some number of failures, and you're interested in what the true underlying success rate is, P. That comes up in millions of different problems. And if you're approaching it like a Bayesian, this is actually a conditional distribution. So for a Bayesian approach to this, this is the distribution of X. X is the number of successes. That's the data that's observed. Given the parameter is binomial. But that's not yet a Bayesian model because we haven't said what the distribution of P is, right? Bayesian means you're doing full probability modeling. So we haven't said what to do with P. So we need a prior, okay? This is the most, I'm not saying this is the correct choice. This is the most popular choice for a prior is a beta distribution. If you've taken Stat 110, you've seen the beta, but if you haven't seen it before, this is what the density is. It's a distribution that only allows values between 0 and 1, which makes sense because the probability has to be between 0 and 1. It has two parameters, A and B, and this is the beta AB density. And these are some plots I took from Wikipedia just showing what some different beta distributions look like this orange one. This is the beta 2.5, for example. So it's actually a very, you don't have to memorize those specific shapes, but I just wanted you to notice that this is just 4 different examples or 5 different examples of betas. And notice that they can take very, very different shapes. So it's a very flexible family of distributions where the value is between 0 and 1. It's a continuous random variable that's between 0 and 1. Okay, so that's the most famous choice, the most popular choice by far. Partly because of its flexibility, but the biggest reason why the beta is so widely used as the prior is not that people really believe it, right? If you go back to these totally subjective Bayesians, they could criticize this and say, well, why do you believe in a beta, right? So the real reason is mathematical convenience. and flexibility. So it has this conjugacy property. So let me tell you what it means to have a conjugate prior. Conjugate prior is a technical term in Bayesian statistics. And it's an extremely convenient property. So what conjugate prior means is that you have some family of distributions for that you're using for your prior. So in this case, we're using a beta. Beta is not one distribution, right? Beta is a whole family of distributions. So you could let A and B be whatever positive numbers you want, and then you have a beta with those parameters. Okay, so it's not one distribution, it's a family. Conjugacy says that if you start out in that family and then observe data, it's still in that family. Okay? So in this case, we're assuming we used a beta prior on the parameter p, and then we observed some data, x, and then we use Bayes' rule to get our posterior. And remember what Bayes' rule says? It says the posterior is proportional to the likelihood times the prior. And if you write, I'm not going to write down the calculation, but if you're familiar with what the binomial probability mass function looks like, which we reviewed in an earlier lecture, and if you're familiar with the beta, which I wrote over there, notice it's p to a power 1 minus p to a power, which is also what you see in the binomial, right? The binomial, you see n choose k, p to the k, 1 minus p to the n minus k. So the point is you have p to a power, 1 minus p to a power, and you multiply two things of that form, it's still of that form. That's the key point. So conjugacy says that the posterior distribution of p is also beta, which is extremely nice. You could imagine if you chose some other prior and you do all this work and calculate the posterior, and it's something you've never heard of, right? And then you go out and get more data, and you use Bayes' rule, likelihood times prior, you do it again, and then you get some other thing that you've never heard of, right? In some different family, right? And then you do it again, and you get something else. Here it's just like you're always working with the beta. So if you understand the beta, you can study basic properties of the beta. It's a famous distribution. You can easily find reference material on the beta. And this says as long as you're working in this context where originally you had a beta prior, it's always going to be beta. The only thing you have to update is the parameters, okay? And the way that you update the parameters is incredibly simple, and it has a nice interpretation. So the interpretation here, this is the prior, right? The way we interpret A and B is we pretend that A was the number of prior successes and B was the number of prior failures. Okay, so if you imagine, that you're studying, whether a certain treatment is successful or failure on, you're trying to treat a certain disease and either you succeed in curing the disease or you don't. Pretend that in the past, so you have some, clinical trial data or something like that, or it could be as simple as flipping a coin or, all kinds of cases where the binomial comes up. This says if in the past you had A successes and B failures, and then here's how you update. This is saying if big X equals little x, it says you had little x successes. So then I'm going to update this success parameter to A plus x, because it's saying I had A successes in the past, and then I have X more successes. So I just updated it, right? And I had B failures in the past, and then I had N minus X more failures, so I'm just going to add them up, right? So it's very intuitive. In some problems, that prior is actual prior data, that you actually had some other literature, or maybe you're doing your own experiment, but maybe in the literature you've seen other people who've done similar experiments, and it's literally is prior data. Or it's a hypothetical, mental construct. And it's also intuitive in the sense that if you really feel like you don't know much about this problem and you don't really have prior data, then you might start with something like beta 1, 1. Or beta 1, 1 is actually a uniform distribution between 0 and 1. But if you actually had a lot of prior data and you were very confident that, it turns out that the expected value of this distribution is A over A plus B. So if you did something like beta of 1,000 comma 2,000, the expected value of that would be 1/3. And that would be saying you have a huge amount of prior data where you have one success for every 2 failures, right? So by playing around with the size of A and B, you're controlling the strength of the prior. You're saying, how important is the prior relative to the likelihood? And if you don't have much actual prior data, you would generally want to choose A and B to be small numbers, maybe between 0 and 1 or between 0 and 2, small numbers. And then, unless the sample size, so n is the sample size, unless the sample size is very small, the likelihood is going to dominate over the prior. So if one person starts out with like a beta, 0.5 comma 0.7, and another person is doing beta 1,1, it makes no practical difference whatsoever if the sample size is reasonably large. Okay, so that kind of gets around these issues about subjectivity. Maybe my subjective prior is beta 0.3, 0.7, and yours is beta 1.2, 1.4. That won't matter unless our sample size is tiny. Okay, so that's a very, very nice properties for beta. Okay, here's one more example of conjugate priors with the normal, right? We've been talking about normal distribution in different contexts. It turns out the normal is conjugate to itself, in the sense that if you have, so here y is our data, and let's just assume that the variance is known to make things simpler. You can do more general models here where both mu and sigma squared are unknown, but since we're just starting out now, so I'm going to keep it simpler, but assume sigma squared is known. The mean is unknown. So what do you do if you're a Bayesian? Well, you're going to give it, the mean is our unknown parameter here, so our focus of interest is on the mean, mu. Okay? It's unknown, so I'm going to give it some distribution, some prior distribution. And, as long as I'm working with normals anyway, let's just let mu itself be normal. This is very closely related to hierarchical models. We briefly talked about like Stein's theorem and hierarchical models and things like that. This actually is a hierarchical model where we have 2 levels of the hierarchy. And, mu has some prior mean, mu 0, and some prior variance, tau squared. This leads to some interesting questions like, well, okay, yeah, you came up with that prior, and these parameters, mu 0 and tau squared, are called the hyperparameters, but how do you know what mu, right now I'm assuming mu 0 and tau squared are known, but actually, how do you know mu 0? It seems kind of unlikely that you know mu 0, but you don't know mu. So if we don't know mu 0, then we want to give that a distribution, right? And that distribution is going to have its own parameters. So the hyperparameters have parameters. And then you say, okay, but I don't know those parameters, and obviously you don't want to get into an infinite regress. And I think there's some interesting questions there that I haven't seen good answers to with like, how do you know how many levels to cut off this hierarchy yet? Do you want to do it? In practice, though, people usually use a 2-level model or a 3-level model, and then beyond that, you don't want to deal with so many layers of hierarchy. Anyway, this is a basic 2-level model, and here's the posterior distribution. So, I won't go through the calculation, but it's not a very hard calculation. It's mostly algebra, and this is what you get. So this is the posterior distribution of mu given y. Notice, first and foremost, it's normal. That's why it's conjugate. Okay, so conjugacy says if you start with the normal prior, you still have a normal prior when you're working with normal data. It stays normal, which is great. You don't have to learn about some new distribution, right? Everything you ever learned about the normal distribution is still applicable here. So it stays normal. And as with the beta binomial, there's a nice interpretation for these parameter values where I didn't write what the formula is for B. I'll write the formula for that before I post this. But what I wanted to emphasize, B is just a constant, which you can write down in terms of the parameters. What I wanted to emphasize here is that it's a weighted average. B is a constant between 0 and 1, which I'll go through later. But my point is that it's a weighted average between the prior mean, mu 0, and the actual data, y, okay? So it's like those puppies, right? With the posterior puppy was a compromise between the prior puppy and the data puppy. That's what's going on here. It says that your posterior mean, so this would be a natural prediction. If you just need to give a single guess based on the data, what's your guess for what the value of mu is? This would be a reasonable thing to do. It's just a weighted average between the prior mean and the data, right? Because saying that the data is saying this and the prior mean is saying this, and if you're really, you're happy that if they're similar, you might be worried if the prior and the data are in conflict. Then they kind of fight it out. You don't necessarily want to give them equal weight, okay, because it depends on how strong your prior is. So like if you are very, very sure that mu is close to 7, and then your observation y is like 12, well, if you're that confident of it, you would still want to estimate something close to 7, right? But if you have a weak prior and say, I don't really know much about mu, that's going to be dictated by this tau squared. If tau squared is large, you're saying there's very high variability in your prior. That means you're very unsure about it, okay? So if tau squared is large, then you're going to end up putting most of your weight on the data. If tau squared is small, it's saying you're very confident of the prior, and you're going to put more weight on the prior mean. Likewise for this sigma squared, right? This sigma squared is saying how precise is your measurement. So if you're able to measure, you're trying to measure mu with noise. So why is this noisy measurement of mu? If your measurement is very noisy, then I'm not going to put as much weight on it. If your measurement is very, very precise, I'm going to put a lot of weight on that. So this is just saying mathematically how to do that, and then how your variance overall updates. And this formula also has an interpretation. In statistics, it's related to something we talked a little bit about with Fisher weighting, that if you're thinking of, you have different. We talked a little bit about Fisher weighting where we had different unbiased estimators that we wanted to combine, and we wanted to weight them inversely proportional to the variances. And what this is saying is that your variance overall in the posterior is going to be dictated by these two variances that we started with. So this is another case of conjugacy. Here's a nice picture from John Cook's website. This one picture, I'm not going to go through everything in this diagram. There's a link there if you want to explore it more. But this one diagram actually contains most of the distributions that are commonly used in practice for parametric statistical models, and then what the conjugate priors are for them. So like, for example, you can see here the beta and the binomial are conjugate, and the normal is conjugate to itself, which is why there's this self loop here. And of course, it depends which parameter you're working with. So this is beta binomial with P. And anyway, the point is not to go through this whole table, but just that most of the widely used distributions in practice, you can find a conjugate distribution. Conjugate distribution makes it incredibly convenient. And in particular, we don't need some of the fancy computational techniques. So we are going to talk a little bit in this course about what's called MCMC, Markov Chain Monte Carlo, which revolutionized Bayesian computing by letting us work with much more complicated Bayesian models than were possible before. But in this case of conjugacy, you often don't even need to bother with MCMC or fancy algorithms. You just, like in the beta case, right? You started with a beta, update based on number of successes, number of failures, it's still beta. You didn't need to do any integral. You didn't need to run some big computation. You just used conjugacy. So that's the nicest case to work with. In some problems, the conjugate prior just feels so unrealistic and you don't want to deal with it, and then you need more complicated methods. But sometimes it's good enough. Okay, so this is an example from that Probabilistic Programming and Bayesian Methods for Hackers book that I linked to earlier. Everything in that book is an IPython notebook, as I mentioned, so that makes it nice as a source of examples to study for this course. So here they were looking at how do you rank comments on Reddit. And the problem is if you just do maximum likelihood for ranking comments, you have, of course, it doesn't have to be Reddit. You have some website where people comment a lot, right? And most of the comments are garbage, and some comments are really good and insightful. You obviously want, the ones that are more valuable and insightful, you want them to go up higher and be more prominent, and the ones that are useless, junk and spam and troll comments, then you want them to go down and kind of buried somewhere where most people won't see them. How do you do that automatically? Well, of course, it helps if it's a site where you can upvote and downvote comments. That's like saying, success or failure. The problem, though, is you don't want to just say, use, what percentage of times do people upvote that comment, right? Because that doesn't adjust for sample size at all. So if you have a comment that only one person saw it and one person liked that comment, that's 100% success. But that doesn't mean, based on that one person, that that's the greatest comment in the history of the internet, right? That just means just one person there. So how do you adjust for sample size? Maximum likelihood would say, if you flip one coin and the coin has probability P of heads, your maximum likelihood estimator if the coin lands heads is 1 for the probability of heads. And your maximum likelihood estimator for the probability of tails, if it lands tails, then you're saying the probability of tails is 1. Just if you're just doing, naive maximum likelihood, which would be stupid, right? That's why you need some kind of regularization. So another way to think of Bayesian methods is that it automatically does regularization for you. That's what the prior is doing. So that's another way to think. Some people, frequentists who used to be upset about all the philosophy behind Bayesian methods are now accepting it as a very nice way to do regularization. For example, the lasso. You can interpret that. It has a Bayesian interpretation as a way to do regularization and kill off a lot of the regression coefficients. Okay, but there are a lot of ways to do regularization. All right, so the model here is just we're trying to model the number of upvotes for a post, and let's say n people chose whether to upvote it or not, and so if we assume that the number of upvotes is binomial, that would be a reasonable model to use. Conjugate prior would be the beta. It's incredibly convenient. And then to update, you start with some parameters, A and B, and then you just update by just saying, okay, I'm going to add the number of upvotes and the number of downvotes to those parameters. But that's not the only way to do it. People don't want to use the beta distribution or Bayesian statistics. That doesn't mean they give up and do nothing on this problem. So another approach is with what's called pseudo-counts, which is like, basically the idea is suppose only one person or a small number of people rated that comment, then we just make up fake data. And a famous method for this is called the Agresti-Cool adjustment, which just says you basically add 2 successes and 2 failures. So it would be like saying every comment on Reddit, let's start out by having 2 upvotes and 2 downvotes, rather than 0 and 0. And that turns out to have some nice properties, okay? But you kind of have to admit it's pretty ad hoc, right? Just like why 2 and 2, okay? So you can make up pseudo-counts and say, I'm going to give everyone 1 success and 1 failure just to get started, just so that at least I'm not saying the probability is 1 out of 1, which is 1, okay? But it's pretty ad hoc. How do you choose those pseudo-counts? Of course, you can say for the Bayesian, how do you choose your prior? And you can say that's ad hoc too. How do you choose the prior? But in general, I was mentioning is, so there's this famous Agresti-Cool method for adjusting to kind of solve this problem in a frequentist way. But as I mentioned, it's harder to extend methods, right? Because it's like that may work well in this problem, but as soon as you add more complexity to the problem, like some kind of correlation structure or some other complexities to the problem, it's not clear what do you do with this +2 +2, right? It kind of feels like a hack that's not very extensible. And also, it doesn't give you the interpretability of posterior distributions. So So Bayesian methods, the result that you're trying to communicate, I would say is generally more interpretable because you're directly quantifying your uncertainty of your unknowns. And that's why Nate Silver calls himself a Bayesian, because he's trying to present, right, the probability of the unknowns. And so you can make, really nice looking pictures like this one. Again, this is from the same example from this IPython notebook book that I mentioned. You get really nice pictures like this of the posterior distributions. So I mentioned that, in Bayesian statistics, the big thing you're trying to do is compute a posterior distribution and then interpret it and check it, okay? So you can, so this is a posterior distribution of upvote ratios on different comments. And you can see for different comments, you don't just have a point estimate, you don't just have one number, there's a 70% chance that this comment is good, right? You actually have a whole distribution. So you can quantify your uncertainty very, very visually. Like for this green one, this green comment only had 10 upvotes and 3 downvotes, so a very small number. So you have a lot of uncertainty, and you can directly see that uncertainty. You're uncertain about how good that comment is based on that, right? Whereas this purple one, right, has 650 something up and 100 and something down. That has a very large sample size, so you see it's tightly concentrated around its mean. There's a sharp peak there. So you can compare different comments just visually, both in terms of where's the mean, where's the peak of each one, and how spread out they are. Is directly quantifying your uncertainty. And then any question, you want to answer about these things, you can read things off of looking at the posterior distributions and looking at probabilities. For example, suppose you wanted to, answer questions about, what's the probability of, so of course you can find out expected values, but you could also find out, what's the posterior median, for example. And a really cool thing about this is you don't actually have to do a lot of complicated math for questions like that. Or, you want to come up with the analog of a confidence interval. Confidence intervals have all these not controversies, but misconceptions in how to interpret them in the frequentist case. In the Bayesian case, the interval you give is directly a probability interval. Usually in Bayesian statistics, that's called a credible interval. But I don't even like that term because it's not that it's not credible. It's that's kind of too weak. Confidence sounds more confident than credible. Okay? Traditionally, frequentists refer to confidence intervals. Bayesians refer to credible intervals. A credible interval is just a probability interval. Right? I could, for example, I could take one of these posterior distribution plots, and if I want to say I'm 95% sure that this comment, has probability of being upvoted, between whatever and whatever, I could just look at this and cut off, let's say, cut off 2%. Cut off 2.5% of the mass over here, 2.5% over here, and find an interval like that. And then I can directly say that's my posterior probability. I can say, given the data, I'm 95% sure that, that this probability that I'm trying to estimate is between whatever and whatever. Okay? It has a direct probability interpretation. Much more straightforward than the interpretation of confidence intervals. And I mentioned posterior median. So if I'm interested in estimating whatever characteristic I want, I basically just read it off from this table, not from the table, from the graph. But I could create a table too. And I'll talk more about the computations later. But in many problems, we don't have to do an integral. We have direct ways to simulate draws from the posterior. Okay, so if I wanted the posterior mean, that is what's the average or expected value for the posterior distribution, in some cases I can just do a calculation, but in some cases many cases, I don't need to do that. I can generate draws from the posterior distribution and just take the mean of those. And if I wanted the posterior median, generate 1,000 draws from the posterior distribution, take the median of those. So there are a lot of problems I can approach that way. And I can get nice pictures like this. So here, again, from the same example, ranking Reddit comments by posterior quantiles. So, this is a large number of comments, and you can make pictures like this very easily using a Bayesian approach where all this is doing is ranking them based on different quantiles. So a median is an example of a quantile. Median means half are above and half are below, right? And other quantiles are just percentiles. So here, they're ranked in terms of percentiles, and the dots are point estimates. So you go way beyond point estimates. Point estimate is when you're just saying, I estimate it as 0.75 or something like that. Okay, but you can capture the entire uncertainty, and then you can choose. Right, the posterior distribution is this whole big picture, and then you need to think about how do you want to summarize it, but then you can basically read it off from there. Okay, so I'll continue with this stuff next time. We're out of time for today. There's obviously more to do with this, so I'm going to stop here. Thanks.